Greetings, everyone. Let's finish up college algebra with applications of exponential and logarithmic operations. So you've already seen these formulas before back when we first started talking about exponentials. We used it for money applications, right? These are both of your compounded interest formulas. The thing is, it doesn't have to just talk about money, but that's still where we're going to start just because it's familiar, okay? Now that we've built up other skills for solving and using logarithms, I can now start asking other types of questions rather than just looking for the after amount. I can ask other questions like, what's the rate and what's the time and things like that. Okay, so let's start with a simple money setup, kind of like the ones we did before. We have some bank account that gives 5% interest every year, right? We've started the account with $300 and we want to know how long until it has $700 in it. That's a good question when you put your money in the bank, right? You put it into some sort of stock, bond, saving, whatever, and you know it's going to gain some interest. The first natural question is, how long is this going to take to grow to whatever it is that you're saving for, right? Okay, so let's do it with two different types of compoundings, and that's because I want to show you both of the formulas here. Compounding quarterly is when n is going to be 4 times a year, so that's going to be this formula. And then continuously is going to be the Shampoo formula, right? Okay, so setting up for quarterly here, the after amount is 700. My principal is 300. 1 plus my rate is 5%, so that's 0.05 over quarterly for 4. And it's raised to the 4 times t power. Now notice the only variable in there is t, right? We want to know how long it would take, so t is our variable. So then I need to start simplifying this. To make it look a little bit more like what we've done before, crunch this this part right here, the 1 plus 0.05 over 4, right? So that's 1.0125. to the 4t. All right. So now the solving method on all of these things is going to come down to one thing. If you need to get into that exponent, then I'm always going to need to get rid of the principal, I'm always going to need to get rid of the base, and then I'm always going to need to get rid of some other multiplied number in there. Okay? So you'll notice that's a multiplication. Bases, remember, we get to the exponent using logarithms, and then that's another multiplication. So I'm going to need to do what I call the DLD. Divide, log, divide. Okay, so in all these applications, you're gonna hear it, DLD. If I'm gonna solve it, right, draw the little face. DLD, divide, log, divide. So here I go. I'm gonna start by dividing by 300. Okay, if I divide by 300, that simplifies to 7/3. 1.0125 to the 4t. Then I do a logarithm on both sides. So that's ln of 7/3 is equal to, now I'm going to put the ln here. Remember how we solve exponentials. If I put a logarithm here, I can drop the power out front. So 4t ln 1.0125. Okay. So I did divide, then I did log. Now I'm going to divide again. What am I going to divide by? I want t by itself, right? So I'm going to divide by the 4, and I'm going to divide by the ln of 1.0125 to both sides. Like that. So these are gone, and I'll have a value for t. Let's punch it up. I have ln of 7/3. Don't forget the 4 and the ln are both in the denominator. You're going to need an extra set of parentheses there. So ln 7/3 divide by 4 ln 1.0125, enter. So I have 17.05, right? And what's that measured in? Well, the interest rate was yearly, right? So that means the time is measured in years also. So if it's compounded quarterly, it'll take just over 17 years to reach the $700 mark. Okay? All right, let's do continuously now. Continuously just means that the interest never stops growing those little bitty pieces, and we have the other formula for that. So if I set that one up very similarly, right, 700 equals 300 for my principal. Then I have e to the power of r times t. So that's going to be 0.05 times t. Right? Now remember, all that's in the exponent. So again, I have to divide, I have to log to get rid of the e, and then I have to divide again. So it's still DLD. If I divide both sides by 300, again I get the 7/3 equals e to the 0.05 t. I'm going to do an ln to both sides again. But here's the lovely part about using the Shampoo formula. It's base e, which is also base e with the ln. These nicely wipe out, leaving me with ln of 7/3 is equal to 0.05 t, which means I'm going to just divide by the 0.05. And then I'll get my value of t. Should be shorter, right? Because compounding gives a slight bit more money per year. Let's find out. ln 7/3 divide by 0.05, 16.95. Years. Okay? So by the time it gets that far out, it's not that much different, right? Of course, 5%, you know, it's not exactly a huge amount, although for a bank account it would be, right? Definitely. Okay, so just like before, those are applications with money. But these formulas, or especially the Shampoo formula, do not have to just talk about money, okay? The first one really kind of does, because this one's sort of artificial, with the n there being, I'm telling you how many times to compound per year or per month or whatever. That's sort of man-made. That's artificial, okay? But this one right here, the continuously, it's always growing a little bit here and there. That's a natural thing as well, right? Populations grow all the time. Radioactive decay decays all of the time, and it's, anything that's based on a percentage of what you have is going to follow this type of growth or decay here, okay? So population is based on the percentage of what you have. You're only going to have as many deaths or births based on how many people you currently have, right? If you only have 10 people, you can't have 20 deaths. If you only have 10 people, you can only have so many kids per year, that sort of thing, right? So it's a percentage-based thing. So is radioactivity. If I have some radioactive rock, it can't radiate more or too less of what it actually holds in it. It's percentage based of what it has currently. Anything that's based like that, anything that has a growth or decay rate based on how much you currently have, is a natural growth or decay, and it will follow this formula. Okay? So here's the first application I can show you for that. Let's say I have some bacterial culture, right? And let's say by some magical process, I know that that culture started with 100 bacteria, okay? I'm just being somewhat generous on one side to talk about, right? Let's just say it's 100 that we started with, okay? Maybe it was one. You know, it only takes one bacteria, right? They can cell divide and grow on their own. So 100 bacteria is pretty generous. let's say that the bacteria culture is growing at a rate of 27% per hour, right? Because they're always growing though. How long until that culture has 5 million bacteria in it, right? So let's set that up. I'm going to use the formula A equals PE to the RT, right? The shampoo formula. So the after amount that we're looking for is the 5 million. The P is the principal, the starting amount, that's 100. E to the 0.27, and then we're looking for time, right? How much time does that take? So we're back to that spot again. I want to solve for an exponent, so DLD, divide, log, divide. So I'm going to divide by 100 on both sides. All that's going to do is knock off a couple of zeros here. So e to the 0.27t. Okay. Now I'm going to do an ln of both sides. Remember, when I do an ln and it's already base e, those are a nice dancing pair. Those two are going to wipe, right? They're actually inverses because they're the same base. So I'm left with ln of 50,000 is equal to 0.27t. And I'm just going to divide by the 0.27. There's the last d, right? So DLD. Let's figure out what that actually equals. ln of 50,000 divided by 0.27. ln 50,000 divided by 0.27. 40.07. Yeah. And what is that measured in? Well, the percentage was a rate per hour. So the time would also have to be measured in hours. Okay? Let's put some context on that. 27% per hour. That's only gaining a little bit over a quarter of your own self every hour, right? It started with 100 bacteria, and in not even 2 days, it's already at the 5 million mark, right? So that's actually quite a fast growth rate if you can gain 27% of yourself every hour, right? We kind of wish our money would do that, right? That'd be awesome. Next step up in these types of applications is when we go a little bit more realistic with the setup, okay? So first and foremost, I want to comment on the shampoo formula, right? The original one that you're given is the most commonly used one, but in my opinion, that particular setup is only good directly and efficiently if you want to solve for either A or P, right? A would be what we solved for way back at the beginning of this chapter. P would be if you had something called present value and you wanted to reverse time and see what you need to start with and to get a certain amount. But really, we don't do a lot of those, right? At least not with the science applications we're doing. Instead, if you're ever needing R or T, if you're solving for those, what I've done is you just do the DLD, divide, log, divide, with the letters. And what you end up with is this other version of the same formula, okay? So this is a better setup for solving for R or T because all I would need to do is figure out which one I need to solve for and then just divide the other, okay? So you'll see me use this other setup a lot in the next few problems here. Okay, so like I said, a more realistic twist here. Typically when you have some sort of application like this, you have to remember in reality, the objects you're measuring don't just whisper out, hey, we're growing at a rate of blah, blah, blah per hour or per month, right? It doesn't work like that. You have to do something to measure the rate, right? And the rate may not even be what you're looking for, but the thing is, the rate really controls the whole problem. So I need to know the rate first before I can actually answer the question. Okay, so let's keep that in mind. The first two sentences here is all just the setup for, hey, go find the rate. All right? Then you can come back and answer the last question. So this pond starts with 90 fish in it. Okay? So they dug it up, right? And then they filled it with the number of fish. And 4 months later, somehow somebody jumped in there and counted all the fish. Who knows, whatever method they used, right? But whatever it is, 4 months later, they counted the fish at 135 now. Okay? So if we're assuming, a percentage growth, which most populations are, and we're not assuming any sort of environmental barriers or any kind of way, because then we'd have to jump over to logistic functions. We're not going to do that. Okay, so we're just going to treat this unbounded growth for now, because it's a big, big pond maybe. All right, so that means first, I'm going to use these two sentences to find R. And then I'm going to ask the question, when will the population reach 200? So step one, find your rate. You need the rate to answer any question in any of these types of problems, right? So I start with 90 fish and I end up with 135 4 months later. Since I'm finding the rate, I'm going to use this formula instead. Remember, they're the same thing, right? But this is a quicker version. It's already got the DLD hooked up, okay? Technically, it's just a DL, actually, because I didn't do the other division yet. But it's waiting. So if I'm going to find R, I'm going to set this up. ln, the after amount is 135. The beginning amount, the principal, was 90. And that's going to equal to R times 4. Remember that 4 is measured in months, right? So any other time-related questions, which that's coming up, needs to be in that same amount. So I'm going to divide by 4 here. And notice I've already got my rate, right? It's this thing. I'm going to write this out, what R is approximately equal to here. But you really don't want to use a chop early in the problem, and then if you can avoid it, okay? So I'm going to put this up here just so that you can see what it should look like. But consider that this is an approximation. Right? This is something that I've chopped off. This is an approximation. I'm going to leave this calculation in my calculator as the last thing, okay? And then in the next part of the problem, I'm going to use the letter R to represent this value. So then when you actually come into the calculator and punch it up, we'll have a much more accurate answer. Okay, so this is an approximation, and in my calculator, it stores way many more digits that'll save us some accuracy. Okay, so here we go. Now I've found my R. Let's answer the question. When will the fish reach a certain population? So that's a question about time. So I'm going to set it up again, right? Except this time I have ln of 200 over 90, right? 200 over 90, because I'm still considering 90 to be the beginning point. If you put 135 in the denominator here, you can still do that. What that would represent is how many months after that 4-month period. But if I put the 90, it's going to be from the beginning, right? When will it have hit the 200? So you could do either one. I'm going to choose to do this one now. Equals R times T, right? R times T. But I know what R is. I just don't feel like putting that yuck monster decimal there. But I know I'm solving for T. So I'm going to divide by R. And in my calculator, instead of R, I'm going to use previous answer, right? So in my calculator, I'm going to type this. Okay, just make sure that this was the last calculation you did if you're going to use the previous answer button. Okay, then I've got ln 200 over 90 divide by previous answer, 7.877. So, time is approximately 7.9 months, right? So practically 8 months. If you were to come back in 8 months, it would be over 200, right? Because it would still technically be growing in that last 0.1 as well. So one other comment I want to make about this is I want you to notice that the R is a positive number here, and that's going to make a difference between whether you have a growth or a decay. Remember, the rate is a percentage-based measurement of how much it changes per time unit, right? So per month, this thing's gaining because it's positive, right? So per month, it's gaining about 10% per month, right? Let's finish up with some alternative applications of this same kind of stuff, okay? Let me introduce a couple of small topics here, half-life and doubling time. These are both measurements of time that it takes for something to either grow or decay by either 1/2 or a doubling of one itself, okay? So let's talk about doubling time first. Doubling time is going to be how long it takes for something that's growing to double in size, right? So from 10 to 20 would be an amount of time that it takes to double, and then that 20 could then double again to 40 in that same amount of time. Because remember, this is percentage based, right? So even though 10 to 20 is only a gain of 10, and 20 to 40 is then a gain of 20, sure, it's a different total gain, but it's the same percentage gain. So in these types of applications, they're going to take the same amount of time because it's doubling in that same amount of time percentage-wise. Same thing goes for half-life, just in reverse. If something has a half-life, that means it is decaying somehow, whether it be radioactively giving off pieces of itself, or maybe some sort of chemical reaction where things are converting into other structures. Or it could be some sort of maybe non-radioactive decay, like in carbon dating, when one type of carbon simply sheds a piece of an extra neutron and becomes a lower form of carbon. They use carbon dating to date things because of how long of a half-life it has. In one way or another, you just have something converting into less of itself, whether it's converting into something else or just destroying altogether. That would ensue something as a half-life, okay? So, for example, if you started with 100 grams of something that's radioactive, and it takes a certain amount of time for that to reach 50 grams, then from that 50, it'll take the same amount of time to hit 25 grams, even though it's a smaller amount. Percentage-wise, it's the same amount of total percentage loss, right? So it has the same amount of time. That is called the half-life of something. It doesn't mean if you put two half-lives together, it's completely gone. No. It doesn't work like that. Every time you hit that amount of time, you've lost half of where that time period started. So technically, by that logic, it never actually reaches zero. So we have to, guess at something that's relatively small enough to be immeasurable or whatever. If you're ever interested in when something's completely gone. Okay, so let's get some applications in, right? What is the doubling time for a population that's growing from 200 million to 300 million in a span of 20 years? So, something roughly the size of our country, whatever. And every, census is done every 10 years. So over 2 census periods, let's say, it increased from 200 million to 300 million, give or take, right? So what is the doubling time? That's a valid question to have as the statistics for some country, right? How long does it take us to double in size? How long will it be before we need to change resources and things like that? Okay, so let's figure that out. First of all, to do the doubling time, I need the rate, right? It's going to be related to the rate somehow. So let's use this information that we have right here to calculate the rate using this, right? Because this is going to help me solve for R. So I'm going to have ln of 300 million over 200 million, right? Now I'm leaving off the million part because they would wipe out anyway in the division. is equal to the rate that I'm looking for times the time, 20 years, right? So my rate is going to be this calculation, this thing divided by 20. That's going to be my rate. And of course, go ahead and punch it in your calculator and get that as your previous answer ready to go, right? Okay, so I have ln of 300 over 200. And then I'm going to divide that whole thing by 20 after I close the parentheses. So I'm getting 0.02-ish, right? So it's gaining about 2% per year, give or take. Okay? But we want to know what the doubling time is. And I've made your life a little easier here. Notice anytime you're involving the doubling time in your calculation, right, with a rate or a time here, it's going to be the ln of 2, because the a is going to be twice as big as the p, right? That's double. So I'm just going to set up ln of 2. I already know my rate, and I'm looking for the doubling time. So I'll be solving for time. I'm going to have ln of 2 is equal to r times t. I already know what r is. I'm going to be plugging that in, but I'm going to divide by r, right? So in my calculator, I'm going to hit ln2 divided by previous answer, and we'll get an amount of time, the doubling time. So ln2 divided by previous answer. I'm getting 34.2 years, right? It's measured in years over there. And that's going to be the doubling time for that population. All right, one more application here. The half-life of Unobtainium, it's not actually an element, right? That's a cool name. I read about that a long time ago when I was doing some of these problems in college, right? The half-life of Unobtainium is 1,279 years. It's a long time for something just to decay half of itself. There are some radioactive things that do last that long, right? There are, even the carbon dating type of things. It takes a long time for the carbon to decay after something's died. So half-lives generally can be, in the thousands of years like that. So how long then would it take a sample of 3 grams to decay into 0.01 grams? Well, this first sentence is all I need in order to get a rate, because it's told you the half-life, right? So for the half-life, I can just set up ln of 1/2 equals a rate times a time, where this time is the half-life, right? Because that's what it is. Half-life is an amount of time. So the t in this setup right here is going to be the half-life. And notice all this is a further application of this same formula. I know that a is going to be half the size of p, so 1/2 works as a reduction there. Okay, so let's start by finding the rate. I know that ln of 1/2 has to equal the rate times the time, 1279 years, right? I'm just going to divide that to both sides, 1279. And now I've got a representation of my rate. Okay, let's punch that up real quick. ln of 1/2 divided by 1279. I'm getting that this is approximately negative 0.000542. Okay? The thing I want to point out to you, this is a negative rate. The mathematics had it already built in, right? Boom. It's supposed to be a decay. It's because of the ln of the 1/2 that you get your negative here. But it's supposed to be there. The rate should be negative. I am losing pieces of this thing, right? It is decaying. Now that I have the rate, I can set up the rest of the question. How long would it take? Well, that means I'm solving for t again, which means I'm going to be using this version. Which, side note again, don't forget, you can still use this version. You'll just have to go through a lot more of the solving, the dividing and the logging, and it's very repetitive, which is not a bad thing if you're learning. But you could also save time by using it this way. Okay, so I'm going to set it up how long would it take, right? So ln of, how long would it take 3 grams to decay into 0.01? Why 0.01? I just picked a number small enough that it would be almost immeasurable and hopefully wouldn't have that much influence radioactively, right? Of course, it's still going to be radioactive, but a piece that small probably would get lost somewhere and you wouldn't even find it again. So essentially, when is it going to go away, right? Okay, and then this is going to be equal to the rate times an amount of time. Of course, the amount of time now is what we're looking for. How long would it take? And I already know the rate, right? We calculated it right here. So I'm going to divide by the rate. And in my calculator, I'm just going to use the previous answer button because that was the last thing I plugged in, right? I'm going to do this logarithm and divide by the previous answer there. So then I have ln 0.01 divide by 3, close the logarithm, divide by previous answer. And I get the amount of time is approximately 10524.659, right? So around, let's just, since it's so many years, we just round to the nearest year. T is around 10,525 years. Right? Long time, right? Well past you and me being here to see it happen, right? Okay, so I hope this helps you with all of the applications that are using exponential and logarithmic setups.